Let us discuss, let us look at some past exam papers that involve standing waves. And as we go with the papers, we can discuss a bit more on standing waves. And let's start from this one, which is from 2018. All right. So let us make it a little bit bigger. On figure 4.1, complete the two graphs to illustrate what is meant by the amplitude A, the wavelength, and the period of a progressive wave. So they show us these two diagrams of progressive waves apparently, but they are not complete, and we need to add to show wavelengths and period and so on, and complete the labels. Okay, so what is meant by the amplitude? Well, let us start first of all. What can this axis be? Well, the vertical axis, the y-axis, has to be displacement, isn't it? By how much each point of the medium is displaced from the equilibrium position. So this must be displacement. And okay, because we need to show both wavelength and period. Obviously, the one must be, the x-axis must be distance, where we can show the wavelength distance, where we can show length, in other words, and this has to be time, so that we can show the period here. So that must be time axis, and this is also displacement. Displacement. Okay. All right, so here we can show the wavelength, here we can show the period, and of course the amplitude, we can show it on both. Okay, amplitude, what can be the amplitude? It's from the equilibrium position, which is here, from this horizontal, from the x-axis, in other words, up to a maximum displacement. So this, for example, this distance could be an amplitude. The same here in the other diagram, that's also an amplitude. Considering that this, on the y-axis we have displacement, so this distance is amplitude in both of these graphs. Now the wavelength, we need to show the wavelength here. To show two points, the distance between the two must be the wavelength. We can take, for example, two peaks, the distance between two peaks. This could be, for example, a wavelength, the equivalent of a wavelength. In other words, the distance between any 2 points in phase is a wavelength. It's not necessarily between two peaks. It could be between two troughs, or could be between this point and this point, where there is one complete cycle repeating itself. So this could also be a wavelength, okay? But nevertheless, the easiest is to show this wavelength between two peaks. All right, here now, here on the x-axis we have time, so here we can show the period. Period is the time taken for one complete cycle, isn't it? So if we choose 2 points that represent one complete cycle, like from there to there, for example, this length on the time axis could represent one period, isn't it? So we have one period here. So that's enough. Now I think we finished with this question. Now in the next question, okay, it's a new kind of beginning. A horizontal string. Okay, so we have a string, and we see that this string is attached at points x and y that are fixed points. So a horizontal string is stretched between two fixed points x and y. A vibrator is used to oscillate the string and produce a stationary wave. Okay, so this figure here shows the string at one instant in time. All right. So if we were to see it in real life, we would see a standing wave, like we would see a shape here repeating. It would be something like that. This is the shape that we would see. We would see the proper standing wave, because something like that, like a blur in between. All right, so this is a standing wave. The speed of a progressive wave along the string is 30 meters per second, okay? The stationary wave has a period of 40 milliseconds. Okay, this is the speed of the wave in this medium, in this string, and the period, this is the period of the wave. Explain how the stationary wave is formed on the string. Okay. How does a stationary wave form? Well, when we have for a stationary wave to form, well, in this particular string, in this particular case, where they give us already this shape, where when the wave, say, moves from left to right and meets this boundary here at y, because this is a fixed boundary, it reflects. And because this is a fixed boundary, a fixed point, the reflected wave actually flips over. So the reflected wave will be upside down. So this dotted line could represent the reflected wave. So the reflected wave, as it moves backwards, now it meets the incoming wave and the two interfere. And we have the production of the stationary wave. So, well, obviously in this case, the reflected wave that moves to the left again, when it meets the other boundary at x, will reflect again and it will flip over. And there we'll have now once moving to the right, the other then moving to the left. And what we see is the standing wave. It is as if we see something vibrating, but we don't see anything moving. And frankly, the energy in this system does not transfer now because it stays in the same region here of between the boundary x and y. So what can be the answer now, the proper answer now, because we talked too much? Explain how the stationary wave is formed on the string. So wave moves along the string to the right. It reflects at a fixed point y, from the wall that is. It flips over and moves to the opposite direction. And as the two waves meet, the incoming and the reflected, they meet and interfere. They superimpose one another. And we have the production of the standing wave. Okay, now a particle on the string oscillates with an amplitude of 13 millimeters. Okay, at time t, the particle has zero displacement. So what does it say now? Remember that here we have the standing wave. Say this is our wave. Actually, maybe we should draw one here because we cannot go up and down the page. So say that we have this kind of 1, 2, 3. This is our wave between the two fixed ends. Let's also draw the other wave, the reflected. Okay, so we have a particle now somewhere, they don't tell us where, which oscillates with an amplitude of 13 millimeters. So it could be any point of the medium. Say it's a point here which goes up and down, and vibrates all the time, up and down, as the standing wave exists in this medium. So anyway, so we have one point in random that oscillates with an amplitude of 13 millimeters. That means from the middle here, from the equilibrium position up to its maximum displacement is 13 millimeters. So at time t, the particle has zero displacement. So in other words, we start from where the particle was there and it's on its way, say, up. So, okay, calculate the displacement of the particle at time t plus 100 milliseconds. T plus 100. Well, remember at t, it's at the zero displacement. So if this is the equilibrium position, the particle is there at t equals 0. And now what is the 100 milliseconds? What happens in 100 milliseconds? We know that they told us actually earlier the problem that the period of this wave is 40 milliseconds. You see that they give us the period is 40 milliseconds. So every 40 milliseconds, the we have a complete cycle starting again. So, okay, if one period is 40 milliseconds, how many periods fit in this 100 milliseconds? In other words, how many cycles correspond to are completed in this 100 milliseconds? Well, if one period is 40, one cycle, in other words, completes in 40 seconds, how many cycles complete in 100 milliseconds? It's a proportion again. So we can find now that 100 milliseconds over 40, this is 2,5. 2,5 cycles complete every 100 milliseconds. So let us understand well what is a cycle here. So for this particular point now that starts from the equilibrium, it goes up and then it comes down to the opposite side and then comes up again to the equilibrium. This would be one complete cycle for this point, isn't it? Up, down, and further down, and then back to there. That is one complete cycle. But now we know that in 100 milliseconds, it will complete 2.5 cycles, not just one. So let's see, where is it going to be after 2.5 cycles? I want to make a better diagram here. So, okay, so we have up, one cycle, then another starts. The second cycle will complete there, and then another half cycle, so it's an up and a down. I hope you understand that this corresponds to 2.5 cycles that complete in 100 milliseconds. You see, be careful, all this path here from to the maximum, back to the equilibrium, down at the minimum, and then back to equilibrium, that's one cycle. So one of these cycles, and then another of these cycles, and another half. Okay, so in other words, after 2.5 cycles, look where the point will be. It's again back at the equilibrium position. Okay, so the displacement of the particle at time t plus 100 milliseconds is 0. I hope you understand that. If you don't, please send me a message. All right. Obviously, the particle here does not move to the right. It moves up and down, up and down. I just have it here expanded so that we can see the cycles. All right. So be careful. Each particle in the medium moves just up and down, up and down. All right. Now, the second question says, now we need to find the total distance moved by the particle, this particle, from time t to t plus 100 milliseconds. Okay, the total distance moved. All right. We know that as this particle vibrates up and down, its amplitude is 13 millimeters, which means this distance here is 13 millimeters. Okay, how many times it moves up and down and covers such distances? Okay, we know that we can go to this shape that we have shown the 2.5 cycles. So we have one distance. How many amplitudes fit here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 times, in other words, completes, during the 100 milliseconds, it moves a distance of 10 amplitudes. So it's 13 millimeters times 10. And this should give us 130 millimeters. So the total distance covered by the particle from t to t plus 100 is 130 millimeters. Okay. I hope you understood how I got this 10. Each of these sections is one amplitude, all right? Each of these sections is 13 millimeters. Goes up and then back and then further down and then back and so on. Okay. Then determine the frequency of the wave. Okay, we can do that's easy because they give us the period. They told us that the period, if you remember, was 40 milliseconds, isn't it? We have a period 40 milliseconds here, 40 milliseconds period, and They also give us the wave, the speed of the wave, which is 30 meters per second. All right, the period, here we need the period. The frequency of the wave, well, the frequency is the 1 over period, isn't it? So this is 1 over 40, but milliseconds, let's change them to seconds, times 10 to the power of minus 3. And this is 25 hertz, it gives 25 hertz. Okay, so the frequency is 25 hertz, here's the unit. Okay, now the next, find the horizontal distance from x to y. Now the x and y actually are the two fixed ends. In other words, it's the length of the string, the string. We need to find the length of the string. Maybe I should try it again because we need to be in this page, not the previous one. So we remember we have here is the x and there is the y. No, this is the x and this is the y. Okay, and we have the string having, this is the equilibrium position. It makes 1. Oh dear. Okay, this is not the best drawing, but I mean, we need though this, the shape of the wave, because we need to look at the wavelengths. Okay, not the best drawing, but nevertheless, I hope we understand that. So we need to find the length actually of this string from x to y, the horizontal distance from x to y. Now, okay, first of all, to find the length, actually, we need to work with wavelengths here. If we look at the shape of the standing wave that we have, how many wavelengths do we see here? Okay, from there up to there is one wavelength, isn't it? Let me show you one wavelength. From there up to there is one wavelength because we see one cycle completes. But we still have another half of wavelength here. So altogether, this L is actually equal to 1.5 wavelengths of this particular wave, the given wave. Okay. Yeah, I see your comment. Let us complete this question and then we can go back to this question again. All right. Now, this is a separate thing. I hope, pay attention, people. Look at this. We need to link the length of the string to the wavelength of the standing wave that we see in the picture. I hope you understand that this from there up to there, it's one full wavelength, because one full cycle. We can see the full cycle, isn't it? And then we have another half of wavelength. This is another half of wavelength. So altogether, the length of the string is 1.5 wavelengths, all right? Okay, now, from the wave equation, remember, because, okay, we found this relationship, which we need to find, it's useful, but we don't know the wavelength though. If we knew the wavelength, we would find the length. Now, how do we find the wavelength? We have enough information about our waves. We know its speed, we know its frequency, its period, we can find its wavelength. So from the wave equation, which is lambda times f, isn't it? Or lambda over period. Okay, so from here, you see, we know the speed because they give it to us. I think it was 30, isn't it? 30, yep, 30 meters per second. It is given. So now, and we also know the frequency, we just found it here. We could also find it from the period. Anyway, so from here, you see, if we solve for wavelength, the lambda, this is the speed of the wave divided by the frequency, and the speed is 30 meters per second. The frequency is 25 hertz. And what is this? This wavelength, well, it's 1 1,2 meters. So there we have the wavelength. And now that we have the wavelength, we can find the L. The distance then between points X and Y, this distance L is 1,5 times 1,2 meters, which is the wavelength, and this is 1,8 meters. And here we found the distance. Here they have the unit, 1,8 meters. Okay, so this is how we found the distance between X and Y. Now, all right, let us see about the previous question. You say, to repeat the displacement question in the previous slide. I hope you mean this question, I suppose, with the displacement of the particle on the string. Yeah, maybe I should start from the beginning completely. Yeah, it's a little bit of a tricky question, isn't it? It is actually, it's not very easy, for sure. I just want you to understand that as we have the standing wave going up and down, vibrating without any sign of propagation to any side, every point on the string, vibrates up and down, wherever we are. So here they tell us just a particle on the string, any particle, from the ones that vibrate that do not belong on nodes, of course, from the ones that move up and down, because at the nodes, the particles stay put, isn't it? But any other particle in between the nodes vibrates up and down. So we just took one particle in random that goes up and down, as we see the standing wave doing what it does, isn't it? So we took this particle in random. The particle at this position will go up to this point and then will go up and down, I hope you understand how it vibrates, up and down, What is one full cycle of the vibration of this particle? One full cycle is when a particle starts from one position, does its own thing, and comes back to the same position. This is one complete cycle. So one complete cycle for a vibration in this case is when the particle starts from zero displacement, it goes up and then it comes down and goes down, and then it comes back again to its to the equilibrium position again. This would be one full cycle, one complete vibration of the particle, isn't it? And also, just one cycle, one cycle that it takes place in 40 milliseconds, because the period that they give us is 40 milliseconds. This takes 40 milliseconds to complete. Also, but they say though, but in 100 milliseconds, where is it going to find itself if it starts from zero? Well, we know that in 40 seconds, milliseconds, it will come back to the equilibrium. We also found that the 100 milliseconds that they talk about, what it does in 100 milliseconds, 100 milliseconds actually it's 2.5 periods or 2.5 cycles. So this is only one cycle. So let's make another cycle and another half cycle. And here's the other half cycle, okay? Of course, I say, don't be confused with the way I draw it. I mean, the particle does not move to the right at all. It moves up and down, but I just have drawn it like that so that we can separate the cycles, so that we can measure things here. So this is the 2.5 cycles that, so it's 40 milliseconds for one cycle, and another 40 milliseconds for the second cycle is 80 altogether. And another half is 100 milliseconds. So the particle in 100 milliseconds, if it starts from the equilibrium, it ends up at the end of the 100 milliseconds, it will be back to the equilibrium position. Okay, that is why the displacement of the particle after 100 milliseconds was at zero again. That is why our answer here was zero. They asked, what is the displacement of the particle at time t plus 100 milliseconds. It will be at 0 because they told us that the t, this is at the 0 position. Okay, does it make sense now? And then they asked us to, in the second question, they say, find the total distance moved by the particle, the total distance moved by the particle from time t, in other words, from the point, from the moment that it was at the equilibrium position up to the moment where it came back to the equilibrium position after 100 milliseconds. And when they say total distance, they mean the distance it moved in its travel up and down, in this travel up and down. In other words, we need to add all these distances, to add them all together and find out the total distance. So we know that each of these sections here, each of these from the equilibrium up to the maximum, or from the equilibrium up to the trough, here you can call it minimum, or the other opposite end, the opposite displacement. All these sections, all the segments are 13 millimeters each, because they told us, they gave us the amplitude is 13 millimeters. So how many of these sections we have? We have one here, then two, then 3, 4, 5, 6, 7, 8, 9, 10. It should be 10 now, but my diagram here has been messed up. It's 10 times that it goes from the equilibrium to this maxima or minima, okay? I see, so I can define amplitude as the maximum disturbance from the rest position. Exactly, that's the definition of the amplitude. It's the maximum displacement of the particle from its equilibrium position. Yes, absolutely. But one thing though, to make sure that we understand here, in this case, we talk about the amplitude of this particular of this particular particle on the standing wave, because in general, when we talk about the amplitude of a wave in general, say we have one wave transmitting, there's no need to be a standing wave, any wave transmitting, the amplitude is the maximum displacement from the equilibrium position. But because in our case we have a standing wave, and particles, I mean, the wave does not transmit, does not go left and right. It's a standing wave, does not transmit. That is why each particle here of this particular wave, the standing wave, has its own amplitude because it cannot change. I mean, this will go only up to there, from there up to there, no more than that. So there are other particles that can have bigger amplitudes in the standing wave, but nevertheless, for a particular point, we can talk about its amplitude. Does it make any more sense now? I hope. Because if it doesn't, just let me know, because maybe I think next week we can continue with standing waves and find also waves, not in strings, but in open and closed pipes, or in pipes, in other words, with sound waves and so on. Okay.